Hi, my name is Aniela Del Rio, and I'm in the SPRS 501 Intro to Space Resources and Exploration class for this fall, and this is my individual presentation based on my research paper. So, first, I wanted to start off with some report information. The title of the paper that I found is Theoretical Bioreactor Design to Perform Microbial Mining Activities on Mars. I've got the authors and publisher listed right there, but this project really has a lot of multifaceted goals. Not only is this project aiming to create a process that will enhance self sufficiency on Mars for future missions to Mars, but it's also meant to decrease the amount of material that we have to take from Earth to Mars on missions and is meant to create a lasting supply of metals such as iron and possibly aluminum, and to also create a biomass that we could use to feed astronauts once we have missions in the future. Next up, we've got some of our project information. So for the resources being used, we've obviously got the in situ resource utilization, especially in space, especially on Mars, as is the whole point of the program of the project. And we've also got mining, specifically biomining. I really had no idea what this was about, so learning about this in this report was really, really interesting, and there's actually so much about it that I didn't know. But moving on to the methods. So we've got the first two here are relationships that are meant to derive and explain how the algae and the biomass would actually grow with the intake of the Martian regolith. I'll go into in one slide a little more information on how the system actually works, but the important bit here is that we've got Martian regolith that will be mixing with this algae in order to create an extraction of ferrous materials that are going to be found inside of the Martian regolith, and then to also create this lasting biomass. And these equations, the Lambert-Beer relationship and the respiratory reaction, are both able to model exactly how much of this algae will be produced and used, the limiting reagents, how much CO2, how much O2 we need to be using, and is really just an encompassing theme for how the process will actually work. Another big part of this is going to be the liquid flow profile investigation, which is basically going to be laminar and turbulent flow that are going to be used to describe how the water is going to be pushing through the system and how this will affect the biomass and also the gaining of these ferrous materials that we need. And then also, this is a mixture of resources from Earth while extracting material on Mars. We are going to be getting this algae initially from Earth and then using that to extract materials on Mars, which again, I will go into a little bit more on this next slide. So basically here in our description of the project, we've got three phases. We have the intake phase, the growth phase, and the reaction phase. So the intake phase is where we go find Martian regolith with known mineralogical composition, and that is loaded into the reactor, mixed with water, and mixed until we get it to reach a certain pH. Next up, we've got the growth phase. So this is when the bacteria or the algae is added, and it's also has light and nutrients used to grow. It's mixed with CO2, which you can see there, and then this mixes with the regolith in order to extract the minerals that we're wanting to gain from this, which is basically the iron. And the gas is added. There's also probes that measure the concentration of this gas, which gives details on how close the process is to being completed. And then we've got the reaction phase. So in this phase, magnets are used on the surface of the reactor, and these are used to extract the metals that are inside of this biomass. And then with the water flow, we use the water to grab all of these metals and to collect them and kind of clean out the reactor, but we're also left with the biomass. And so then we've got both of these things left in separate containers that we can now use separately. And like I was saying with the project findings, the first one of which was that we can extract metals from the Martian regolith, specifically the iron. And this is super, super important as a big part of the work is to be able to actually extract this metal in a form that we can use and have available for projects. And then the other one is the biomass that can be used to feed astronauts. And so then this is left, and we can use this material to make sure that astronauts have sustainable living environments when they're going to be doing a mission to Mars in the future. Our next question is, do the findings make sense? In my opinion, the findings are all like they definitely all make sense and they're all very well sourced. A big part of why I think this is because the equations that we were using for all of these processes are things that are actively being used on Earth and that we actively understand here. And I've always thought that when we have processes here on Earth that we've been studying and investigating for a long time, and you just adapt them to the needs in space, that's when it's going to be most useful and also most successful because you already really know what's going on here. You're just adapting it to a smaller, you're just tweaking small things for a greater purpose. Um, and so, yeah, again, like they had all of this information in the paper, and it definitely looks like it's all making sense. And then we've got the technology that they're using for the modeling. So they have modeled the reactor and how the process would actually work, especially with a system that I had not heard of called COMSOL, COMSOL, which is a laminar and turbulent flow simulator. And so then this whole system has already been created and simulated using all of this software. And when you create a full prototype of something, that is going to make sure it's going to be way more successful in the future. We've learned that here at Minds with every single other project I've been a part of. And so, yeah, I think that the findings and the research that they came out of this project that is clearly very well researched and very well investigated definitely makes sense. And finally, we've got our consideration of space resources. A lot of aspects are being considered. Like I said, the system is multifaceted. We are considering every single part of this. All of the materials being used can be used for different things. We are creating biomass for astronauts. We are finding and extracting ferrous materials such as iron. Like all of this is being used with each other, and so that everything here is being considered equally. And then there's also a lot of things specifically from the paper that are being considered that I wanted to talk about. So, first of all, they mentioned specific locations on Mars and specific craters that have high concentrations of mineralogically rich material, like so mineralogically rich Martian regolith that they would be able to use for this that would yield the highest amounts possible of iron for this project. So that was already something that they took into consideration. Another thing was food safety for the biomass. They've run a ton of tests in order to determine whether or not this could actually be consumed by people without lasting effects, which I thought was a really great consideration of how this would actually be employed in space. Another one is, like we talked about in class about a week ago, there we're actively as a planet trying to find evidence of life on Mars. And with bringing a system that would potentially cause contamination with biomass already on Mars, we want to make sure that we keep these systems separately so that we don't get any false positives when trying to determine if there ever actually was life on Mars. And they specifically mentioned in this project, in the research paper, that they would have a closed system that would then keep every bit of the biomass inside unless it was being used, which would then also be in a closed situation since the astronauts would have to be consuming it. But this was a really great consideration because it's also considering other research questions and other aspects of space resources that we haven't yet answered and want to make sure that we have the ability to do in the future. And then finally, they also tested whether or not this would actually be beneficial and be a project that would work. And a big part of this was if that they needed to make sure that the iron extracted would outweigh the resources consumed. And they specifically found that 0.14 grams of the nutrients would yield 1 gram of iron, and that we would be gaining 11.7 grams of iron per hour with the system, with the specific Martian regolith that they're planning on using. And all of these considerations together are definitely a really great way to look at the problem as a whole. And I would argue that the team in charge of this really did a great job of coming at this from a multifaceted angle and considering everything that they had to make this project successful. Thank you for listening, and that was my project.